familiar part of the French landscape, it is now conquering distant territories in Africa and beyond. We take it for granted, but the TGV almost didn't see the light of day.
For long-distance travel, no one gave the train a chance.
While old modes of transport were being discarded in the post-war boom, the potential for train travel seemed boundless.
In the 1960s, a French engineer was offering amazing speeds of 300 to 400 kilometers per hour, which is unreal.
Meanwhile, the engineers developing the first TGV high-speed train were wrestling with a complex, real-world challenge.
We wondered whether we were being too optimistic. Would we be able to operate at 260 or 270 kilometers per hour?
How did the TGV revolutionize rail travel for a world hungry for speed?
It was a kind of revolution. In Europe, nothing quite like it had been seen on the tracks.
On the very first day, there were 75,000 passengers.
What innovations in engineering, track design, and route planning came together to ensure the TGV's success?
If you go too fast around a tight bend, you'll go off at a tangent.
While TGV is one of the safest high-speed lines in the world, accidents can happen.
The driver had just enough time to apply the brakes, but it was too late.
Although France has been spared in passenger-related tragedies, other countries aren't as fortunate.
A storm had caused the signaling and control systems to fail.
As one of the best-performing trains on Earth and holder of the world rail speed record, the TGV runs circles around its competitors at over 600 kilometers per hour.
The underlying principle is a magnetic field creating a blade between the locomotive and the rail.
In the fiercely competitive international high-speed market, TGV has continued to evolve, with the latest model offering a more streamlined profile. Now, 3D animation and interviews with experts are your first-class ticket to experience the exciting technological and human stories that propelled this trailblazing train, the TGV. This is high-speed rail's latest offering. After many years of hush-hush design, the new silhouette is finally revealed. Behind the elegant and sleek new profile lurks a host of technological innovations.
The aim of this project was to get a head start on the competition. There are many factors in which this TGV offers very significant progress. It is a train that will mark its era.
The Alstom plant in eastern France. This is where the pieces of a highly strategic puzzle are manufactured and assembled, the engine for the new TGV. It is 4 meters shorter compared to the previous generation, but just as powerful. And much more streamlined to allow considerable energy savings. 20% less than the TGV duplex.
20% is huge. It's a real breakthrough. We worked on a range of parameters to achieve this reduction. 2/3 of this is achieved through the train's aerodynamics.
We have experienced high-speed campaigns from recent years to incorporate all the know-how into this TGV and produce a train that is pretty efficient from an aerodynamic point of view.
This translates into a nose with an atypical shape. We worked on the bogie fairings and the fairing of the pantograph zone. A lot of tweaks on the right and on the left to produce an improvement in aerodynamic drag.
Over to the west, 800 kilometers away, is the Alstom site. The first engines manufactured in the East were taken across France to be assembled with the carriages manufactured in the La Rochelle workshops. With powertrains and carriages in tandem, like an athlete made of metal and stuffed full of electronics, it is ready for its first training sessions.
We're starting to assemble the first prototypes, for example, full-scale trains that will enable us to carry out static tests in the first instance, followed by a series of dynamic tests over a period of 18 months on the very high-speed networks.
Before 2024, the year of the commercial launch, the prototype must be assessed in a wide range of tests. The new TGV is pushed to its limits, being subjected, for example, to Sahara-type temperatures to test its air conditioning. Comfort, performance, safety. Everything needs to be scrutinized and approved before it is allowed to run with passengers on board. Meanwhile, production continues. 115 trains are to be delivered to the SNCF, which has decided to call its new model the TGV-M, M for modular.
This is the first TGV on which we can put 7, 8, or 9 carriages. Our old TGVs had a fixed number of 8. Here we can put the first or second class carriages and can easily transform one into the other. In terms of passenger space, we put in seats, but if we want to add luggage compartments or bicycle spaces, these are the same fixing points, so the train's configuration can be changed quickly and easily.
The 9-carriage train gives TGV-M a significant leap in capacity, with a potential 740 seats, which translates to 20% more passengers, all with reduced fuel consumption. Further major advances have been made with the tens of thousands of parts and cables that make up the innards of the train, all of which have the potential to fail. In the new TGV, every part will be continuously monitored by sensors, which send information via artificial intelligence to maintenance services.
On existing TGVs, we carry out what we call preventative maintenance. That is to say, we know that a component will last for 8 years. So after 8 years, all the train components are changed. Predictive maintenance disregards the projected lifespan of a component. The use of sensors produces physical and electrical readings that allow the beginnings of anomalies to be detected before the equipment actually fails. In first-generation trains, people came to the depot with USB keys to assess the health of the train. But with the later trains, we had daily data readings. Now we can transmit gigabytes of data 10 times a second. This potential is already being widely exploited in the aeronautics industry, but it is still being developed in the train industry.
Maintenance, energy consumption, capacity, modularity. A wide range of innovations is on offer, some of which are confidential trade secrets, as is the case with the new component that will be part of the architecture of the new trains. With the TGV-M, Alstom and the French National Railway Company seem to have optimized the TGV's industrial heritage to the full. It's a fascinating technological history that spans many decades. Why, in the mid-1960s, did only a handful of diehards believe in the future of high-speed rail? How did the TGV come into being in a world that considered the train a relic of the past?
Back in the 1960s, governments all over the world were in love with motorways and jet aircraft.
Trains were on the way out, except for regional services, particularly trains serving the greater suburbs. But for long distances, everyone thought that the train was doomed to obsolescence.
While the whole world was contemplating the end of long-distance train travel, Japan proved the naysayers wrong, developing the first high-speed train, the Shinkansen.
When the first part opened between Tokyo and Osaka in 1964, It was a real railway revolution. Trains were running at 210 kilometers an hour, much faster than anywhere else in the world.
2 years after the Japanese Shinkansen was put into service, the French railway company tentatively set up a research department to develop a high-speed train project.
The SNCF research department had 75 people. At that time, the equivalent research department for Japanese trains had 1,000 workers.
At the time this department was set up, French trains ran at an average speed of 160 kilometers per hour. One benchmark the handful of high-speed researchers could look to was the SNCF's flagship model, the Capitole. This train had been running between Paris and the southwest of France at speeds of up to 200 kilometers per hour since 1967, but that was widely regarded as the top speed for any locomotive.
At the time, every country in the world was convinced that pretty much the ultimate speed for railways was somewhere in the 200 kilometers an hour range, and that any improvements would mean doing things differently. Hence, the development of the German and Japanese magnetic levitation systems.
In France, people remembered the world record of 1955.
320. 325. The figures on the speedometer are impressive.
The SNCF, though, decided to focus on developing existing rail technology rather than the magnetic levitation train.
In 1955, 2 locomotives were accelerated up to the amazing speed of 326 and 331 kilometers an hour. And so French engineers knew that trains could run much faster, so there was lots of potential.
One of the ways to increase speed was to use trains equipped with turbines that run not on electricity, but rather oil. More powerful, lighter, less expensive to run, able to reach speeds of 225 kilometers per hour, these trains inspired the future TGV.
These were the famous turbo trains that ran on the line between Paris and France's Atlantic coast. They were hugely successful. They were so fast, they were known as the teacher turbos, in reference to teachers who lived in Paris and taught in Normandy.
What was needed was a train with independent traction, since it was less expensive than an electric train, with the attendant line electrification. So the idea was to do something really new by harnessing the kind of technologies used in aeronautics.
For the TGV, the biggest development borrowed from aeronautics was turbine technology.
Researchers turned to helicopter turbines. There was no new turbine specifically designed for the TGV 001.
The same turbines that equipped record-breaking military helicopters in the 1960s.
The idea was to equip high-speed trains with aeronautical turbines, whose lightness gives a very high power density. The first experimental train was equipped with 4 turbines. At a little more than 4,000 kilowatts, it had more power than existing locomotives.
Fueled by a mixture of gas and kerosene, the turbines drove an alternator to create an electric current. The current, in turn, powered the traction motors located in the train's wheel systems, called bogies.
None of the parts operate on reciprocating movement, whereas in a diesel engine you have cylinders with pistons that wear out, crankshafts knocking, etc. This was beautiful. It was going to be something really extraordinary.
March 23, 1972. Something exceptional rolled out of the Alstom workshops, codename TGV-001. TGV for Turbotrain à grande vitesse. Its shape was revolutionary. This was light years away from the design of the then running locomotives.
The search for higher speeds forced us to address the issue of resistance to forward motion. You don't need to be an expert in aerodynamics to grasp that the cube-shaped locomotive is problematic. So we put it through the wind tunnel and found the ideal profile for 300 kilometers per hour.
This is the first time we've seen a profile with a slightly longer nose. It was more streamlined compared to previous locomotives, so from an aerodynamic point of view, it really was revolutionary.
This completely redesigned aerodynamic design was the work of a man from a completely different world, automobile designer Jacques Couper.
We brought in someone who had designed sports cars. We tried to adopt any good ideas, including those from outside the world of rail travel, which was a relatively new direction. And that's how we came up with the TGV 001.
We needed a train with a dynamic, powerful shape, given that it would be traveling at speeds of around 300 kilometers per hour. We have a luggage compartment at the rear because in this train, passengers cannot keep large luggage with them. They have to put it in the hold.
The TGV developed at the time was modeled on an aircraft cabin, and, as in aeronautics, the engineers sought weight reductions wherever possible. Polyester laminate fairings, aluminum bulkheads, plastic air conditioning ducts. Everything was designed to that end. One area where the weight saving was considerable is the wheel system. The bogies were now located between the carriages.
The 5 carriages were coupled together to make a fixed-form train. This was a revolution.
Bogies were usually placed beneath carriages with symmetrically arranged units. In these high-speed trains, for the first time, the bogies were placed between rather than beneath the carriages, with the help of an intercirculation ring. Fewer bogies means a lighter train, one that is both less expensive to produce and more aerodynamic.
An articulated train has the advantage of having far fewer bogies, which are areas of turbulence, strongly contributing to aerodynamic drag, creating forces that work against the train's progress.
Boasting this new kind of aerodynamics, testing for the turbotrain à grande vitesse began on the rail network. From the very earliest trials, it reached speeds far in excess of those achieved by the Capitole and even the Shinkansen.
The first test runs were in eastern France, the region around the plant where the train was assembled. We quickly reached 260 kilometers per hour, which was the commercial objective. But we were soon close to 300 kilometers per hour, which was absolutely extraordinary.
With the TGV, the French National Railway Company now had a champion to restore its image. Except that after a few months of testing, clocking up tens of thousands of kilometers, one component of the train was beginning to worry the engineers.
In November 1972, at 240 kilometers per hour, instabilities were noticed in the bogie, which began making irrepressible movements.
If you push a shopping cart a little too fast and the caster is not well adjusted, it can start to judder. The same can happen with a high-speed train bogie.
We wondered whether we were being over-optimistic. Could we really run trains at 260 or 270 kilometers per hour?
While the SNCF was sweating it out with its prototype, it suddenly had to deal with an outsider, appearing as if from nowhere. With its futuristic shape, it made a big impression.
In the 1960s, a French engineer came up with a project called the Aerotrain. The proposed speeds of 300 to 400 kilometers per hour were completely surreal at the time.
The TGV 001 was beaten to the punch by the Aerotrain in terms of speed, which in 1969 had already reached a speed of 422 kilometers per hour. What were the pros and cons of the two projects that were getting the transport industry so excited? Why did the Aerotrain manage to seduce so many decision makers to the extent of overshadowing the TGV?
The Aerotrain was an outstanding project and rather visionary.
There is no question that the Aerotrain gave us a challenge.
This is Jean Bertrand, the man who pushed the SNCF out of the spotlight in the mid-60s.
No component is in contact with the track. The machine can go at any speed.
A brilliant graduate of the prestigious engineering school Polytechnique, he filed several patents for the aeronautics industry.
Jean Bertrand, a great engineer, had the idea of developing an air-cushioned train.
While a new mode of transport, the aerotrain did not reinvent the wheel. On the contrary, it dispensed with it altogether.
It is a train for which the support functions are air cushions, meaning the body of the vehicle reposes on air cushions inflated with air. A very small jet of air maintains the required pressure. Transversal guidance is handled by vertical cushions enclosed around a concrete rail.
The infrastructure is a monorail in the shape of an inverted T, about 10 meters high. To propel the machine, 2 turbines drive a propeller more than 2 meters 40 in diameter. And to brake, Bertrand used the design adopted by a number of aircraft, harnessing reverse thrust affected by changing the orientation of the blades.
The aerotrain is very simple, and that's why it was such a great idea.
The first prototypes came out of Jean Bertrand's workshop in the early 1960s, with many improvements incorporated thereafter. While the design was indeed brilliant, the concept had a number of weaknesses right from the outset. In fact, the aerotrain was like inventing a car that goes much faster than any other, but cannot be driven on highways.
The major problem was that it necessitated the building of completely new infrastructures. It was not compatible with boarding in some Paris train stations. Imagine a viaduct running from Paris to Marseille, with a terminal in Paris on a concrete viaduct. This would be absolutely unthinkable. The aerotrain had another disadvantage. It needed to be turned around. Turning one unit around is fine. You can do it in a single turntable, but when you have 5, it's another matter.
Unlike the aerotrain, the turbotrain à grande vitesse could run in both directions and pull into any station on the conventional existing rail network. Moreover, in terms of capacity, the two technologies were leagues apart.
You have to consider that a TGV has 500 seats. With 2 of them together, you can have more than 1,000 seats. This was a vehicle with 80 seats, so economically, it was a very expensive line for a really poor capacity.
Not only did the aerotrain carry fewer passengers, it also consumed more energy.
Maintaining the air pressure to ensure lift and guidance, even at a standstill, consumes a lot of energy.
Despite its obvious drawbacks, the aerotrain eclipsed the TGV, and the futuristic project had the attentive ear of the public authorities.
It enjoyed a novelty appeal and excellent lobbying, fueling the enthusiasm of well-placed people in government circles.
The TGV was a development entirely financed by the SNCF, whereas the aerotrain was backed by the public authorities.
The aerotrain had the ear of the government of the day because a good government is one that innovates. This was an era of gargantuan ventures, of progress, of the unprecedented.
The speed performance of the aerotrain was so impressive that the government signed a contract with Jean Bertrand to build a line in the Paris region running between the suburbs and the capital's business district. The future for the aerotrain seemed bright. Then in 1974, the contract was suddenly canceled. What prompted this U-turn by the government of the day? A few months earlier, in the fall of 1973, oil prices began to soar.
With the oil crisis in 1973, the price per barrel increased 4-fold. For railways, which have diesel locomotives, the impact was only 4%. But for cars, it was 40 to 50%, and for aircraft, around 70 to 80% of the cost.
The gas-guzzling aerotrain fell from grace as the wind turned in favor of the SNCF. At one of his last cabinet meetings, the French president at the time validated the project for a high-speed line between Paris and Lyon, a decision made easier by his belief that the TGV-001 would run not on gas turbines, but on electricity.
When Roger Guibert, the chairman of SNCF, presented the Paris-Lyon high-speed line project, Pompidou said to Guibert, "By the way, your train is electric, right?" Guibert paused for a moment and said, "Why, yes, Mr. President." The next day, he told his engineers, "Well, guys, we got it all wrong. It has to be electric."
Although the SNCF and Alstom had won the industrial battle with the aerotrain, they now had to roll up their sleeves to produce a train compatible with the new economic reality.
This wasn't in the plans at all. Everything had to be refitted, but that's what saved the TGV. It was electric.
While the new TGV was based on the architecture of the turbotrain à grande vitesse, the helicopter turbines had to be replaced by a more complex electrical system.
The drive engine of the TGV is still based on 4 major functional blocks. The first block captures the energy from the catenary via the pantograph. The second block acts as a transformer, reducing the 25 kilovolts of the catenary to a voltage of around 1000 volts. The third block is the electrical converters, which transform this catenary energy into energy and motor control. And the last block is the motor, with the kinematic chain that drives the axle.
While designing this new train, the engineers took the opportunity to solve the problem with the bogies, identified during testing for the TGV-001.
In a locomotive, the engine is simple. It's right in the bogie. For the TGV, to lighten the bogie, the engine was mounted into the body.
The commercial running speed for the new TGV was meant to be 260 kilometers per hour, and the first Paris-Lyon line was already planning 300 kilometers per hour. Carrying the train's empty weight of 350 tons along with passengers at such a speed requires a commensurate amount of power.
A train is like an electric coffee grinder. If you power your coffee grinder with 180 volts instead of 220, it will run a little slower. For a train to run at 300 or 320 kilometers per hour in service, it needs enough energy to run at that speed.
On a high-speed line, the TGV receives a current of 25,000 volts, compared to the 1,500 for a conventional line. The current is carried by a copper wire called the catenary. The energy is conveyed to the train via a jointed framework called a pantograph. This contact zone between the catenary and pantograph is a vital component.
Energy passes between pantograph and catenary through a surface area the size of a 1-pound coin.
As with conventional trains, the TGV's collector head running on the catenary is fixed at an angle. This creates a zigzag effect to prevent the catenary from always rubbing in the same place and sawing the pantograph head in two. In addition to the usual lateral movement, in the case of high-speed trains, vertical movement of the pantograph also had to be incorporated.
The catenary is rather like a vibrating rope, so you need a good match between the speed of the train and the speed of the wave. This is what we call critical speed of the catenary.
If incorrectly adjusted, the pantograph loses contact, causing arcing.
The faster you go, the higher the frequency of the oscillations, so the collector head needs to be very light. Hence, a 2-level pantograph was developed for the TGV.
The first level is sufficient for reduced speeds on the conventional network, when the TGV is leaving or entering a station, for example. The second level of the pantograph needs to be able to adjust to the much more rapid oscillations of the catenary on a high-speed line.
A small, light pantograph with improved contact with the catenary was a new development.
With its lighter bogies, new electric motor, and revised pantograph, the TGV was ready to roll. A few months before its launch, the SNCF began a communications blitz.
During my presentations on the equipment, I was often asked whether the TGV would have seatbelts. I realized we needed to show we had room for maneuver.
To show what it could do, the TGV challenged the legendary 1955 record. To that end, the SNCF chose a standard train set identical to all the other leaving the Alstom factories, only with slightly larger wheels and a more sophisticated gearing system. While the engineers knew perfectly well that they could easily exceed the 260 kilometers per hour, they still had to overcome the previous 331 kilometers per hour record.
Waiting for permission to depart.
Depart.
On February 26, 1981, the voltage was boosted to 29,000 volts. 3 carriages were taken away to lower the weight, and the speedster was pushed to its limits.
Pull, let's go.
The 1955 record was easily surpassed. With the media watching for the slightest slip-up, the TGV began clocking up the numbers, one after the other.
373, 74, 75, 76, 77, 78, 79, 380. We have reached 380 kilometers per hour.
At 381, we reduced the speed because the catenary was lifting. In France, it made the headlines. I remember the headline in the newspaper at the time, "The Fabulous TGV."
That demonstrated to other people in the railway, and particularly to the public, that running at really high speed was quite safe. There was a huge margin between the maximum commercial speed, which was 260 kilometers an hour, and just what had been achieved with this special test at 380.
On the strength of this new world record, the TGV Paris Southeast Line was inaugurated 7 months later amid much fanfare by the recently elected president, François Mitterrand. With its futuristic lines, the 200-meter-long orange snake was causing quite a stir both inside and outside the country.
It was a kind of revolution in Europe. Nothing quite like it had been seen on the tracks. The TGV train itself was full of innovations. It was quite lightweight, it had a low-slung body, and it had a lot of interesting equipment on it, like in-cab signaling, so the driver didn't have to look at any line-side signals.
The other thing that struck people was its color, orange. That was the designer's choice. It was the orange era. It became the color of progress. It was going to be very difficult to abandon it for the Atlantic network, which wanted to use blue.
With the introduction of the TGV, the journey time between Paris and Lyon was now just 2 hours and 40 minutes, compared to more than 4 hours previously. It was a colossal time saving and a big challenge to air travel, which had constantly been gaining market share in the 60s and 70s.
When the first TGV line was opened, the engineers said they were expecting 17,000 passengers a day. Are you sure? Don't be silly. Let's say 16,000. On the first day, there were 75,000 passengers.
It was an immediate commercial success. The price difference between the TGV and air travel was enormous. A TGV ticket cost 200 francs, while a plane ticket was around 800.
In 1981, French travelers were introduced not only to a new train and reservation system, but also to a revolutionary infrastructure. No freight trains. No conventional trains. This was the first line in Europe reserved for high-speed travel.
It was a massive project in so many respects. The first being civil engineering, hydraulic structures, earth structures, engineering structures, 13-meter platforms, layers and sublayers that needed to be absolutely perfect.
In setting up this first line, the engineers were able to take advantage of the TGV's principal trump card, its speed.
The Paris-Lyon line was a real breakthrough, inasmuch as with conventional heavy trains, it had previously been better to dig a tunnel or make a cutting, but the TGV's inertia allowed it to handle gradients, then use the descent to recover speed.
When you're in the cab at that speed, you can see that it's moving in all directions. A freight train couldn't climb the slope.
It was built with a lot of steep gradients, a kind of switchback, and this avoided the use of tunnels, which are very expensive, saving about 15% of the cost.
Although the TGV was capable of negotiating slopes of 3.5% compared to only 1% for conventional trains, it needed to avoid curves as much as possible.
The line layout had to be compatible with the speed, meaning the faster you go, the straighter you have to shoot.
You can't travel at 270 or 300 kilometers per hour with a small bend radius. If you go too fast around a tight bend, it's like riding a bicycle or driving a car. You'll skid and go off at a tangent. Simple mathematical formulas that show that every speed has a minimum bend radius. On high-speed trains, the smallest radii are something like 4,000 meters.
This radius can exceed 6,000 meters for lines running at 350 kilometers per hour. Such radii give the TGV a much higher margin of safety in terms of derailment. It could potentially go faster, but does not.
It's a question of passenger comfort. That's to say, we want passengers to be able to go to the bar and return with their drinks, etc., without falling and spilling them on other passengers. So this is what limits the train's speed in a bend.
Although built to be as rectilinear as possible, the line is much like a traditional track, only more so.
The engineers worked a lot on the ballast, which is made from pebbles. They not only used more of it, they also used very, very hard ballast that can withstand the effect of extremely strong dynamic loads.
Each sleeper weighs around 300 kilos, so they are very heavy, enough to drown in the ballast. They aim to move as little as possible.
On this base of volcanic rock and concrete, 432-meter-long rails are laid, making them 100 meters longer than the height of the Eiffel Tower.
The welded rail sections can be made extremely long. Also, the rail is heavy, weighing 60 kilograms per meter. For conventional lines, the weight is only 50 kilos.
In order to supply the TGV with power via the kilometers of copper wire in the catenaries, another colossal project involved the construction of electrical substations.
A substation is the end power outlet. This is the connection to the RTE network, the Electrical Energy Transport Network.
Each station transforms the 225,000 volts of the RTE network into 25,000 volts for use by the TGV, with substations required every 50 kilometers or so.
If the network strays too far from a substation, the current passing through the cables will weaken. So instead of having 25,000 volts, you might have, say, only 21,000 volts.
The first high-speed line was completed in 1983. Then in 1989 and 1990, the TGV was introduced in other towns near Paris. In 1993, it came to the north of France and the Channel Tunnel the following year. Provence and the French Riviera had to wait until 2001. Now, with more than 2,800 kilometers of high-speed lines, France has the fourth most extensive network in the world, after China, Spain, and Japan. In France and elsewhere, the network is constantly expanding all over the world.
There are projects in Eastern Europe, there are high-speed lines in Morocco and in Saudi Arabia, and there is a high-speed line under construction in California. I think there's a lot of potential for more high-speed lines.
High-speed rail travel is viewed in such a positive light because it offers so many benefits. Journey times are sometimes faster than air travel. It has a much better carbon footprint, and all this with an extremely high level of safety.
On dedicated high-speed lines, the railway is very safe. There are no level crossings, the signaling and train control is nearly always automated, so there is no human error. And if you look back over the history, there have only been 2 serious accidents.
What caused these deadliest accidents around the world? Why is TGV one of the safest trains in the world? What technological innovation has enabled it to avoid derailments? On January 30th, 2003, a TGV train traveling at more than 100 kilometers per hour collided with a heavy goods vehicle stuck on a level crossing. Only one axle came off the rails. The rest of the train remained on the track. December 21st, 1993, a train from the north of France to Paris flirted with disaster while traveling at 300 kilometers per hour.
The earth covering the remains of some First World War trenches collapsed. The TGV came through. The opening was several meters wide. But the track held firm. The train was not derailed.
Faced with such conditions, a conventional train would have crashed or derailed and concertinaed. But the TGV remained on the track. The secret of such resilience lies in a component that has existed since the birth of the very first train, the bogie. By changing the position of the bogies to make the train lighter, the TGV designers made the train more rigid without realizing it.
The articulated train has another advantage that we hadn't considered at all, which is that as a single block, a fixed-shaped snake, it can only be derailed with difficulty.
The articulated train set is a plus compared to conventional trains where carriages are connected by buffer couplings, which are much looser and break much more easily. An articulated train forms a kind of spine.
Despite being an articulated train, the TGV is not immune to accidents, although they remain relatively rare. One of the greatest fears for a TGV is the prospect of a head-on collision, especially on a conventional track, as happened in the French Alps in 1988.
A TGV was traveling on a conventional line at 110 kilometers an hour. Around a bend, a convoy was struck on a level crossing. The driver had just enough time to brake, but it was too late. The driver was killed, and the tragedy forced us into a rethink. It triggered all the modeling and crash tests carried out afterwards to produce a train that responded better to events external to the TGV system.
2015, Eastern France, this time on a high-speed line. This incident was the greatest tragedy to affect high-speed rail travel in France, but it did not involve a passenger service. A train being tested on the new TGV East line approached a bend too fast. A train left the tracks and ended up in a canal. 11 people died.
Unfortunately, we had a terrible accident with a train that was being tested, which means all the safety devices that monitor the speed of a commercial train had been deliberately bypassed for testing purposes.
While rare, fatal high-speed passenger accidents have occurred outside France. In Europe, the worst incident occurred in Germany in 1998 on the Munich-Hamburg line. An equipment failure at a wheel triggered a chain reaction that led to all the carriages being derailed. The accident killed 101 people and injured 88. In Asia, the Wenzhou disaster in 2011 killed 36 people and injured nearly 200, undermining confidence in the safety of the Chinese network.
A storm had caused the signaling and control systems to fail, and the staff decided to use manual control, and maybe they weren't as familiar with the procedures as they should have been, and it ended up with one train colliding with the rear of another, and it happened on the viaduct.
Since its inception, The TGV has had a dozen or so accidents, but not a single life has been lost among the billions of passengers transported in all of its history. Along with the Japanese Shinkansen, it is the safest train in the world. Is that enough to guarantee export success? It's not that simple. Which countries have chosen to adopt the TGV? Who are the historical competitors and the new challengers? How does it manage to hold its own in an ultra-competitive market?
Today, 1 out of every 2 high-speed trains in the world is an Alstom train or one with the Alstom high-speed technology.
In 1990, the TGV passed the mythical 500 km/h mark and set a new record. Hitting a speed of 515 km/h, the iconic high-speed train astonished the world, winning over countries planning to launch a high-speed rail service. After Spain in 1992, it was South Korea's turn in 1994. And while the Spaniards only bought the actual train this time, South Korea took the whole TGV system.
There had been competition between the Japanese, the French, and the Germans, and the French won it, and part of the deal was that they would transfer their TGV technology to South Korea.
The Koreans chose the track technology, the signaling, and the Alstom train, so they really embraced TGV's technology in its entirety.
After 10 years of Franco-Korean cooperation, the KTX was launched in 2004. 6 years later, France was once again exporting its TGV system. Trains manufactured by Alstom were shipped and made their first trips along the Moroccan coastline in 2018.
Morocco had the first high-speed system in Africa, and it was French.
Infrastructure, signaling, maintenance services, TGV duplex. The entire TGV system was bought for the line between Tangiers and Casablanca. Winning a contract worth several billion euros was all the more satisfying in such a highly competitive niche market.
Who are the TGV's competitors? Well, aside from what you might call the historical competitors, the Germans with ICE and the Japanese with successive versions of their high-speed train, there were also new competitors, notably the Spanish.
In Spain, the Talgo company has high-speed trains which they exported to Saudi Arabia. So there's quite a lot of competition there.
Among the new players in high-speed rail, one in particular was developing rapidly: China.
The Chinese railways have built a huge network, about 40,000 kilometers, and the trains run at up to 350 kilometers an hour, the fastest in the world. Potentially, it is a huge competitor, but so far it has not succeeded in breaking into the markets, which have been dominated by French, German, and Japanese suppliers.
For the time being, they are focused on domestic development. But it is very likely that they will be competing on the international markets one day soon.
In the global race for the faster high-speed land travel, one project that was thought to be dead and buried has been resurrected: the maglev. In Japan in 2015, it reached a record speed of 603 kilometers per hour, with the plan to link Tokyo to Nagoya in 40 minutes, meaning 286 kilometers at a speed of 500 kilometers per hour. It achieves such astonishing speeds thanks to magnetic levitation.
The principle is based on a magnetic field, creating a blade between the moving train and the rail, made from concrete in this case.
When the maglev gains speed, the wheels retract. The train levitates thanks to copper coils located in the side rails, which interact with magnets incorporated into the train. Propulsion is produced by other electromagnets on the sides of the train, interacting with another series of coils. The permanent inversion of north-south polarities makes the maglev move forward. While the technology is spectacular, like Jean Bertin's aerotrain, it is not without certain drawbacks.
There is only one high-speed commercial maglev operation, that's in China, in Shanghai. The infrastructure involves using huge quantities of copper to generate the magnetic field. So that's a problem simply because of the cost.
Ignoring the significantly higher energy cost compared to the train, the main handicap of the maglev is its non-operability with existing networks.
The question of networks is a strategic issue, and some are reluctant to embark on the construction of high-speed lines. This is the case in England, Italy, Poland, and in the United States, on the flagship line between Boston and Washington, passing through New York and Philadelphia. Alstom managed to establish itself in the 1990s with a train that could reach high speeds on a conventional line. A contract was renewed in 2016 for a similar train in an improved version.
It's a potentially large market. We also know that there is a well-established and powerful air lobby, which is probably why it hasn't developed so much. The tilting train, as it is called, was a big factor in Alstom's success in winning this American market.
The tilting train is technically capable of leaning into bends, thus saving considerable time on winding routes.
It's a train where inclination is safely controlled according to the speed and the curve of the bend.
Using sensors and an onboard database, the train anticipates approaching bends. Once the information has been analyzed by the onboard computer, signals are sent to the mobile pantograph and to the bogies, which are tilted by means of cylinders. The system allows travelers to endure greater centrifugal force without feeling any motion sickness.
The advantage of the tilting train is that it allows you to go about 20 to 30% faster without having to rebuild the track.
With more modest speed targets, perhaps the rail industry is finally entering the age of reason. The latest model, the TGV-M, is capable of running at 350 kilometers per hour, but its main selling point is not that it goes faster, but that it is more fuel efficient.
I think it's come just at the right time because energy costs have spiraled up and lower costs for operating trains would be absolutely vital for the future.
The ecological challenge is a real opportunity for rail travel because it is the mode of public transport that offers the best carbon footprint.
Decades of know-how in high-speed rail travel has enabled SNCF and Alstom to perfect their trains, generation after generation. Their latest offering is better connected, more economical, and more environmentally friendly. A TGV in tune with the times. In the coming years, an unprecedented development of high-speed lines all over the world is expected, and the TGV may well be holding all the cards.